Now for the solution of part 2 of question 6b, how do we find the distance between lines L1 and L2? So we found that line 1 and line 2 are parallel, so we can draw this out. We'll call this one line 2, we'll call this one line 1. Well, the distance between them is given by that orthogonal vector. Now, if we choose an arbitrary point here and another arbitrary point here that we call P1 and P2, we can decompose this vector into a projection of vector P2 minus P1 onto the direction vector of L1, which is D1. And then we can find the orthogonal complement by taking P2 minus P1 minus the projection vector of P2 minus P1 onto D1. So step 1, find P2 minus P1, P2 minus P1, P1. We can pick two arbitrary points, but we have 2 points given by the vector form of line 1 and line 2. So line 1 is 2, 2, 0. So we'll put 2, 2, 0. And then coming all the way back up to the top, the point on line 2 will be 1, negative 3, 0. 1, negative 3, 0. Take the difference between them. We get P2 minus P1 is equal to 1, negative 5, 0. Okay. Now let's find the projection vector of P2 minus P1 onto D1. So to remind ourselves of the equation, the projection vector P2 minus P1 to D1 is of the form D1 dot product P2 minus P1. Then we take the dot product of D1 dot D1. This is a scalar that we then multiply by D1. You can put vector arrows over all of these vectors. So let's break this down into parts. What is the dot product of D1 dot P2 minus P1? So let's remember what D1 is. D1 is 1, 3 halves, 1. 1, 3 halves, 1. Dot. P2 minus P1 is equal to 1, negative 5, 1. 1, negative 5, 1. So this is equal to 1 plus negative 15 over 2 plus 1, 2. I have caught myself in an error. There is a negative sign. 1 minus 2 is equal to negative 1. And so we have to change that to that, and this becomes negative 1. And this here is not negative 1, negative 5, 1. It's negative 1, negative 5, 0. So this becomes a 0. And so we get negative 17 over 2 is the dot product of D1 and P2 minus P1. Okay, what is D1 dot D1? We get 1, 3 halves, 1. dot 1, 3/2 1. This is equal to 1 plus 9 over 4 plus 1, which is equal to 17 over 4. Now, substituting our dot product values into the projection vector equation, bring this down here, we are going to get d1 dot p2 minus p1 is equal to negative 17 over 2. d1 dot d1 is equal to 17 over 4, and so if we're dividing them, we can simply multiply by the reciprocal, 4 over 17. Would be a scalar that we then multiply by d1, which is 1, 3/2 1. This is equal to negative 2, 1, 3/2 1, which is equal to negative 2, negative 3, negative 2. Okay, so we found the projection vector, and now we need to find the orthogonal complement, which is p2 minus p1 minus the projection vector. So p2 minus p1 minus the projection, p2 minus p1 to d1. This is equal to, let's not copy this incorrectly, negative 1, negative 5, 0. The projection vector is negative 2, negative 3, negative 2, so this will come out to plus 2, plus 3, plus 2. This is equal to 1, negative 2, 2. Okay. And now, so that is this vector, but the question is, what is the magnitude of this vector? How far are lines 2 and line 1 from one another? You can find that by taking the magnitude minus projection 1, p2 minus p1 equal to the magnitude of 1, negative 2, 2 equal to the square root 1, negative 2, 2 on 1, negative 2, 2. And this is equal to 1 plus 4, 4, while taking the square root of 9, which is equal to, because really we're taking the positive square root of this value, positive square root of 9 is equal to 3. And so the final answer is that the distance between these two lines is 3.